So welcome to this lecture today. I hope you're all doing well. Let me just recall what we did last time, or maybe the most important notions we had there. So one, we started with a Brownian motion Rn. That was a stochastic process with values, stochastic process Bn with values in Rn, which starts at 0. So B0 is constantly 0. Then it has independent increments, and the distribution of these increments is always a centered Gaussian with variance U times the identity matrix. So that's the covariance matrix, and yeah, U here is the difference between the time, the time here and then the other time, and we assume that the paths are continuous. Okay. And then the other thing that we defined was a filtration. That's a family Ft indexed by positive real numbers T of sigma subfields. Or yeah, maybe you're more familiar with the term sigma subalgebra. So it's a sigma algebra, which is a subset of our big sigma algebra F. It has the following property: it's increasing. So if I have an S that's smaller than T, then the sigma algebra Fs is contained in the sigma algebra Ft. So they get larger and larger, and yeah, I guess you're all familiar with these concepts from probability theory or measure theory, that if you get larger and larger sigma algebras, that means that you get more and more information. So somehow these filtrations, yeah, they collect more and more information with time. And then associated to these filtrations, we have the notion of a martingale, which is an important class of stochastic processes. So xt is a martingale with respect to some filtration ft. If the following is true, so xt is ft measurable. So that means that yeah, all the information contained in the random variable is also contained in the sigma algebra ft. So that's actually what. So if I have a stochastic process such that just the first condition is true, then we call the stochastic process an ft, a process adapted to ft. That will come again up soon. And then the second property is that yeah, we want all xt's to be integrable. And then the most important condition, so the first ones are in some sense technical. The most important condition is the last condition here, which means that if you condition xt on all of the information that's contained in fs, then you get back xs, where if the t is bigger than s. Okay, and yeah, we will actually discuss examples later in the exercise session, but maybe just to mention the most important example here. So if bt is a Brownian motion, let's say on R, a Brownian motion on R, then I can cook up a filtration. Namely, if I set ft to be the sigma algebra generated by bs, where s is smaller than t, for t bigger than 0, then yeah, so this definition defines a filtration. So with this we get that this is a filtration. Okay, and also we will see in the exercise that's a little bit, well, it's a very short proof. If one knows how to do it correctly, then also the bt is a martingale with respect to this filtration. Just write ft, and then yeah, maybe last one. If I take bt squared and subtract t, then this is also martingale with respect to ft. Okay, and then proves This we will do today in the exercise session. Okay, and then the main topic today will be, like, maybe you recall that we wanted to make sense of these stochastic differential equations, which meant that which were in some sense stochastic differential equations where you had a noise term, and which in some sense we will now model by this Brownian motion. But instead of defining a differential equation directly, we will proceed indirectly in the sense that we will define what it means to integrate with respect to Brownian motion, and then we will rewrite the differential equations as integral equations, and that's how we want to proceed. And therefore, the first thing that we will discuss now is how to integrate with respect to Brownian motion, and there all these things will appear again, like filtrations and martingales and Brownian motion and these things, and that's why I introduced these notions first. So the next section, or the next section of this introductory part to stochastic calculus is called the Ito integral, and we will in particular also see what the interesting feature of the Ito integral is also the Ito isometry, which is quite important. Okay, and so just to fix the setup, that will be the setup for pretty much the rest of the lecture. Well, today is we start from a Brownian motion, and well, basically we have three things. So we have it's better to separate this a bit. So BT is a Brownian motion. Yes, we've defined above, and then we start from some filtration, which is not necessarily the filtration that comes from the Brownian motion, but we want the Brownian motion to be a martingale with respect to this filtration. Okay, so that's a filtration such that, of course, everything lives on the same probability space, such that BT is a martingale. With respect to this filtration FT. Maybe you can take a picture now, then you have these examples if you're interested, and you need a bit more space. And then the third one is the stochastic process that we want to integrate with respect to Brownian motion, and for that we require the following. So that's the stochastic process XT, and that should be an FT adapted process. I'll define what this means. So as you would expect, it means that i.e. XT is a stochastic process and XS is FS measurable for all positive S. Okay, so that's the definition of stochastic of an adapted process. So I don't want to go into too many details there. I guess this is quite clear. And then we need some kind of regularity condition on this process, such that we will be able to define the integral. Namely, you consider the pathwise integral, so xs squared dx. This is smaller. Well, this is finite for all t bigger than 0, and this probability should be 1. Okay, so this integral here is like, you can think of it as in a normal Lebesgue sense, defined as in Lebesgue sense, for example, or so. So we assume that the xs is measurable in the variable s, And then you can look at this as a Lebesgue integral. Of course, then the resulting object here is still a random variable, so we can consider the probability that this is a random variable with a finite value, right? Okay, so these are the three assumptions for the setup, and then we can define what it means to have how we define the integral or the E2 integral. Then so we take capital S and capital T maybe. So we'll define a finite interval. We define the E2 integral. Yeah, and that's somehow of the process xt with respect to the Brownian motion we specified above, t. And that's given as follows. So take the integral from capital, big S to big T, and then I take the process xs, that's now small s, dbs, and it's defined as the following limit. So I discretize this interval, so I sum up from k equal to 0 up to n minus 1. I evaluate the process x at t minus s times k over n, and then I take the difference of the Brownian motion. So in some sense, this is how you would compute a Riemann integral. But the important point is that we evaluate so yeah, this is somewhat a Riemann sum in some sense, but the important point here is that we evaluate always at the lower end of this interval, right? I mean, here you evaluate your integral or this difference here on an interval, namely from t minus s times k over n up to t minus s k plus 1 over n, and then the stochastic process you integrate, this you evaluate at the lower end of the integral at the lower end of the interval, and that's actually important. And there's a whole notion, if you evaluate this here at a different place, you get some other kind of stochastic integral. So it's important to do that. I can, of course, again not go into the details here because we are, well, in the end we are studying random matrices. So this here will be a formalism in the tool to get certain results. And I should also say something about the convergence here. So maybe you want to take a picture first.
I'm sorry,
and this convergence will actually be in probability, and this comes from the fact from this kind of condition. We could replace this condition here by assuming that the expectation of this random variable here is finite, and then you would get convergence in L2. That's how I defined it on the homework. So we will do that today. And yeah, here I should say that
I'm sorry, Fluent will
limit exists.
the index.
You can show that's the let's write it in the sense of convergence in probability. This in the sense of convergence in probability, and it's also independent of this discretization. So it's independent of how I choose these intervals to discretize this big interval. Let me also remark this, and then I say something about how this is obtained. So this integral is independent of the chosen discretization. Of S, of this interval big S, big T. Okay, and how is this proven? Well, this is the usual the usual sense that you first make sense of this for some kind of simple processes which look in some sense like characteristic functions. And then you extend that to all processes, and that way you can prove these kind of statements under this condition. Okay, and maybe maybe I list a few properties of this integral. So maybe I do that as in the form of a lemma. So maybe the first thing is that, so the stochastic process that we get out of this integral, if we integrate from 0 to t, xs dbs, for positive t, this is a continuous process, so it has almost surely continuous path. And well, I should be maybe a bit more precise. So actually you have to change, you can replace this stochastic process by a continuous version of it, which is almost surely continuous. But yeah, this is again a bit subtlety, which I don't want to go into. But so you should always think of, if I write such an integral, then this is a continuous process that will be important. And then we have the usual rules for integration. So if I integrate such a thing here, then I can well, just integrate it up to u when u lies between s and t, and then I have to add the rest. So for s smaller u smaller t. Okay, and then we I see there was a question. Maybe I'm not quite sure I understood. Maybe you can explain to me where you want to add an s.
In the limit.
Sorry, I could not hear you. Can you repeat it again?
In the limit, there's x with index t minus s,
yes,
k over n, and maybe there we should add s. Because for k equal to 0, this is not the end of.
You mean I didn't choose the discretization correctly? Yeah, that's correct. So yes, that's true. Yeah, I forgot an s. Good point. So does it look correct now? So I think now it seems it looks correct to me. If you have more complaints, then please let me know. Thanks. And yes, so that's the correct form of this discretization. And yeah, so this was the first form was the first first property told you that how to split up if the interval, if you want to integrate it only on part of the interval. The second property is about linearity. So of course this is a linear integral, as one would expect. Yeah, so here the alpha is a constant, and yt the same properties as x. Yeah. As xt. Okay. And then there are yeah, well, maybe now is a good time to take a picture. So there are two more properties. So this process is not only continuous, this process which I gave you here, but it's also a martingale with respect to the filtration that we fixed in the beginning. And then we also have this Ito isometry. Okay, so let me give them to you now. So the fourth one is that if I look at this process xt bt, then this is a martingale with respect to the filtration we fixed before. So there it's important that the Brownian motion was also a martingale with respect to this ft. And then the last one is the Ito isometry. So that's often very handy for several computations. And it says the following: if I take such an integral and I square it, and I want to compute the expectation of this, then this has a really nice form. Namely, it's the expectation, and then if I take the process that I had before, I have to square the x inside, and then I integrate dt. Okay, and here of course we need some yeah, I guess this is also understood that such that if this is infinite, then also this will be infinite. Okay, so these are the properties of the integral that well, this is just to give you an overview and give you some feeling how these things work. And now we want to use that, yeah, maybe you want to take another picture. And now we want to use that as a way to introduce stochastic differential equations, namely to formulate them in such a way that we get that we formulate them as integral equations. So that's what I want to do next. So we will look at these stochastic differential equations. And then an important relation to analyze them is actually the Ito formula, which is some kind of chain rule for these stochastic differential equations. Okay, so yeah. Yeah, so recall that we are interested in actually studying some kind of differential equations. Which of the following forms. So somehow we have a dxt is equal to some coefficient sigma xt dbt plus alpha dxt dt. Okay, so this is of course for now it's all formal, but I will define it in a minute what it means. So yeah, xt is some stochastic process. And then bt is a Brownian motion, and yeah, sigma and alpha are functions. And how should you think of it? Well, you should think of it that the xt is a function of the Brownian motion bt, and yeah, and it also depends on time. And then this relation should explain to you how the xt changes if you change, if you change the Brownian motion or if you change the time. So it's, yeah, in some sense it depends on these two variables, and then you want to see how the function evolves along this yeah, well, longest evaluation of the evolution of the time and the Brownian motion. And now from the previous section, we somehow know how to integrate, at least with respect to this Brownian motion. And now we will actually just reread this as a reread this differential equation and use it as a shorthand for an integral version of this. So maybe I call this 1. So from section 2, so what we just discussed before, we know how to integrate with respect to Brownian motion. And therefore we can interpret this. And this we now use to interpret. We use this to interpret the following integral equation. The integral equation. So yeah, you should think of it as if the bt were an ordinary variable and you wanted to integrate this here, then you will get the following. So you would ask for xt being x0 plus, and then you would have integrals of this type, bt plus, and then the integral alpha t xt dt. Okay, so that's what I want to call 2. And yeah, you should note that this here is now everything here is well defined. So if the xt is ft measurable, then this here is ft adapted. So this integral is really defined in the sense of, so I specified in the section before. So whenever this is so whenever we have an equation of this form, then we actually mean something like this. So I will make this more precise in the next definition. And of course, if I give you a stochastic process X and a sigma and an alpha, then this is, you can somehow try to check this. I mean, at least, well, for now we did not compute too many integrals yet, but in principle you have definition for all of these quantities, so you can check whether the X and the bt that I give to you satisfy this relation. So that's a precise mathematical statement. And yeah, maybe now is a good time for a picture. And then I define stochastic processes which can be written in such a form, or in a very similar form. Next in next definition, and they are called Ito processes. So that's the definition 3.5. And it says the following. So I look at the stochastic process X. That's an Ito process. If it has the following form, if xt is x0 plus the integral of some function u us ds. So yeah, well, omega here is the, well, maybe I should also have an omega here. So that's the argument on the probability space, and then here I have an integral v fs omega ds dbs of omega. That we want to call 3, and we need the following assumptions. So we want the xt again to be ft adapted. So that way we need that u is ft. So u is now a function that depends on the probability space and also on time, on the t. So it's all, you can also think of it as a stochastic process, and that should be adapted. So that means that just to make it very clear, if I evaluate at an s and I consider u of s just as a random variable, then this is fs measurable. For all s. And yeah, I need some regularity to make such that this integral is well defined. So for example, it's enough to require that this is finite for all non-negative t with probability 1. So that's the assumption on u. And then for v, we have the very same. So v is ft adapted as well. And now we need a little bit more regularity for the v. So namely, we need this with a square. And the probability that if I integrate this as omega squared ds, then this is finite for positive t with probability 1. Okay, so yeah, I think we still have that, and we write like the three in some short form, namely the short, somehow maybe called differential form. Differential form, and then we write so dxt is u dt plus v dvt. Okay, and yeah, so maybe this is a good moment to take a picture. And the point now will be that then of course, yeah, if you remember like integration theory or standard differential calculus, then it's somehow important to have a chain rule to be able to do many transformations. And here in this kind of stochastic setup, there's also a chain rule. Namely, it's it's called Ito formula, and that's what we want to look at next. And it gives you an expression for how to transform. Well, first of all, it will tell you that if you take a function of such a process, of an Ito process, then you get another Ito process, and it explains to you how you can compute the coefficients, can compute the coefficients of this type. And so yeah, maybe I should give some introductory sentence. So the basic tool for further analysis of Ito processes so the next result. And yeah, as I said, it's a chain rule. It's one analogon of the chain rule. If I take a function g of t and xt, and x is when xt is an Ito process. Okay. And that's the following theorem. As I said, it's called Ito's formula, or the Ito formula, and it it looks as follows. So I start from an Ito process, which I write again in its differential form. Okay, so the U and V satisfy the assumptions that we had before. And then I start from a function G, which is a function of two variables, so of time in 0 infinity. And for now, we do everything in a one-dimensional setup. And yeah, so it's a C2 function in time and in space, or well, space here is the value of the xt. And then I want to look at the stochastic process yt, which is g of t xt. So this is also an Ito process. And we can compute its differential form. And it looks as follows. So dyt is, so this now looks at first maybe a bit complicated, but it's actually the most simple way of writing it. So if we would have so we have a partial derivatives here, xt dxt. So what does that say? So well, it says that if I want to compute the differential of yt, then I have to take a partial derivative of g with respect to t, and then I get a t derivative here. And then if I take the differential of g with respect to x, so with respect to the second coordinate, then I get an xt here. That would be the standard way. But now in the stochastic calculus, there's an additional term because we have the stochastic derivatives, and this additional term comes from it comes in the following way. It's a second derivative with respect to the x coordinate, the second coordinate, and then we have to take in dxt squared, where I will explain to you how to compute this square. This is of course it's a notation that doesn't have a deeper mathematical meaning, because it's defined as follows, where dxt squared, which you should think of as the product of two of them, this is computed as follows. So you just plug in the previous differential form of this of the dxt, and then you apply the following rules. So if you multiply two time derivatives, or you multiply a time and the Brownian motion in whichever order, then this term vanishes. And the only one which does not vanish is the one when you multiply the Brownian motion derivatives, and that gives you a dt. Okay, so that's in some sense the analog of this Ito formula, of this Ito isometry formula. And so this is this Ito formula. As I said, this is the new term which you don't expect, or which is not present in the standard calculus. And and that gives you many new features, and we will use this now to compute the stochastic integral. And that will also show to you that because of this term, also the stochastic integrals behave differently. So yeah, I guess maybe you take a picture now, and then we will use this now in an example to compute some, well, kind of basic stochastic integral you could be interested in, and then we will see why this is helpful. So yeah, maybe I should mark this first. So the Ito formula it can be used particular to calculate stochastic integrals. This I want to show you in the next example. So we want to compute the following integral, 0 to t ds dbs, right? That of course satisfies all assumptions. The bs is a Gaussian random variable, so that's as nice as you can imagine. And in some sense, well, this is the integral in the standard language or in the standard differential calculus. This would be the integral x dx. So that's of course trivial to solve. And actually, this will be somewhat helpful because we will choose a function gtx before, namely 1/2 x squared. So that would be the standard integration. That would be the standard result if I integrate x with respect to x. And now we want to use this Ito formula to compute the differential form of this yt, which is gt bt, which is 1/2 bt squared. So if we now get that the yt is only this integral, then we directly computed it and we guessed correctly. But I can already tell you that you will have another term. So let's go through this. So we follow Ito's formula. With this we get the following. So I take a dyt, then I have to take the dt derivative of g and put dt, but well, this does not depend on this, so this is 0 times dt from this. Then I take a an x derivative of g and put a dx there, so that's of course non-zero, and the x derivative, when I plug in bt, this is bt dxt. Okay, and sorry, x is b. And then I have the second derivative, which is of course a constant, namely this is 1/2. So this is 1/2 times bt squared, right? And now we have to use all of these rules, and then, well, none of this applies. We just have this here. So this will give us another dt. So in the end, what we get is that this is bt dbt plus 1/2 dt. Or if I integrate it, I can write it in the integrated form. So that means that, well, let's write it out once. This is this. Yes, TBS plus 0t 1/2 ds. But on the other hand, this here is 1/2 bt squared. So that means 1/2 bt squared, this here is 0, is equal to 0t bs dbs plus this other guy, which of course gives you a 1/2 times t. So that way we computed the so that way we computed the BTS 0t bs bs. So this has a term which looks like the thing that you would naively expect, but then there's some kind of correction term. So this is particularly an example that shows that the stochastic integral is a bit different from the, yeah, it does not trivially behave in the same way as one would expect. So the stochastic integral behaves differently than the usual integral. So yeah, let back for Riemann integral. Okay, so maybe now's a good time for a picture. And then before the break, I just want to make one remark, namely what we assumed in the Ito formula was a bit too much. So what did we assume? So we assumed that the G is a C2 function. But actually, if you look at the formula, and you could also see it from the proof if we would go through it, you only need a first derivative in time, and you only need the first two derivatives in x in the stochastic process in the second variable here, and also you don't need this on the whole space. But if you know a priori that your process xt does not go into the whole space, but you have an open set which contains all values of xt, then this will be enough. So this I want to fix in the last remark. This has just 2 small points, and then afterwards we will make a break. So for the Ito formula, the following suffices. So sufficient that, so the first I want to say that G is in C2 of 0 infinity for the space variable, and U sorry, 0 infinity for the time variable and U for the space variable, where the U is an open subset of R. And we need to know that the xt does not leave U for all t and for all omega in the underlying probability space. And then the second thing is that gt of x is C1 with respect to t, and C2 with respect to x. And then here after the break, I want to translate this to the multidimensional setup. Actually, the whole formalism, as I wrote it there, is essentially already tailored to the multidimensional setup. And and then we will see that what these stochastic differential equations look like that we want to study, and say something about the existence and uniqueness of these equations. And that's what I want to do after the break. So maybe we can continue, let's say, let's say 10:20, and then we will translate these things. So the integration, Ito's formula to the multidimensional setup, and study there, and then define stochastic differential equations in this setup, and I'll give you some kinds of solution. That there are 2 types of solutions: weak solutions and strong solutions, and then we will see how these whether they under what conditions they exist, and whether you have some uniqueness. And then finally, I want to give you an outlook how we will apply this to the random matrix setup. Okay, then let's stop here and see you at 10:20. Okay, then let's continue. So as I said before, we now want to go to the multidimensional setup. Let's just quickly recall what we've done. So the basic observation was that there is a way to define a stochastic integral with respect to Brownian motion. And actually, you will see that this formula here, it also makes sense, say, if if X is a matrix valued process, and then B's are vector valued Brownian motion. So far everything was one dimensional, although I didn't really stress it because it was not really essential. And then we will have the same way we can define Ito processes in this Ito formula in the multidimensional setup, and then we will continue with this, and then we will get this some sense systems of differential equations, and then we will be able to apply this to the random matrix setup, where we actually have these kind of equations. We will have one for on the matrix level, that was this process which I already mentioned, and then on the eigenvalue level we will have also a system which looks somewhat more complicated, and which is called this Dyson-Brownian motion. Okay, but yeah, as I said, to get started, we now extend the formalism which I've introduced in this sections 2, 2 and 3 to the multidimensional setup, and yes, I already indicated to a multidimensional setup. And the basic observation here is that that is definition of the integral. So let me just recall it. So I had an S up to T, X as the BS was defined at this limit. T minus S K over N plus S B T minus S K plus 1 over N plus S minus K over N plus S. Okay, so this also makes sense if X and or B are vector / matrix valued. Why is that? Well, I mean, you can interpret this here also as a well, if X is a matrix and B's are vectors, then this is a matrix vector multiplication, and then you have, of course, component-wise the same as before, or you can think of both. Well, you can think of this being a scalar and this being a matrix or a vector. Then that's also clear. And then or you can also assume that both of them are a matrix. Then you can also multiply them. So that's completely, that makes sense. And or you can of course also think of doing all of these things just component-wise. So now we will therefore introduce an n-dimensional Ito process. So yeah, I will maybe make it a little bit less formal. So now I have the argument. So X is now n-dimensional. So I want to put the time argument as the argument of usual function, and the index of the component I want to put as a lower index. This is an n-dimensional Ito process if the following is correct. Namely, if there is an M, which will be the index of the Brownian motion, such that if I look at the components, or yeah, M will be the number of Brownian motions, so I can look at the components of X and they satisfy the following relation: dxk dt plus g1 to m v k j dbj. For all k from 1 up to n, where so now I have an m-dimensional Brownian motion. The Brownian motion on Rm. So yeah, I guess you can all convince yourself that the Brownian motion on Rm is the same as having m independent Brownian motions, and the coefficients have to satisfy the same conditions as we had in the previous lemma. And vk and uk and vkj satisfy. Yes, maybe you should just take a picture now, and maybe you can take another picture once the definition is complete. So yeah, uk and vkj satisfy the same conditions as we had before. They satisfy the conditions on u and v definition 3.5. So yeah, that meant that they were adapted, and we had this integrability condition, and yeah, k here runs from 1 up to n, and j from 1 up to m. Okay, and then we will want to write it in some kind of matrix vector notation in matrix vector notation. We write the following. So maybe the xt u dt plus v dbt. We have the following. So u is a function with n components, a vector with n components, and each of them are functions of t and of the randomness. And v is a matrix, an n times m matrix. And then the dbt is the differential with respect to an m-dimensional Brownian motion. Okay, so maybe now is a good time for another picture. And yeah, as we saw before, the main tool now is the Ito formula, and this is here the same. So I will now, the next thing will be the multi-dimensional Ito formula, which will be exactly the same. I will write it in the exact same notation as before in this differential form. And that, yeah, as I said before, that's somewhat the most compact way to write it down and to memorize it. But maybe as a homework, you can also write it out in integral form. Then it's, well, just to convince yourself how to work with these formulas, and to convince yourself that this is really an honest expression. So yeah, we start from an Ito process, which I want to write as before, the dbt in this differential form. So that should be an n-dimensional Ito process. And yeah, I will use the same notation for the matrices and the vectors. So that's why I say here as above, because I want to write it down now in components, then everything looks a bit better, or looks a bit more transparent. So, and yeah, as before, I have a function of the time variable, and which starts on Rn, and maybe say goes to Rp. BC2, And I want to write its components as follows. Components GTX is G1 T of X up to GP T of X. Well, maybe it's more consistent if I write it as a vector. And then we have the following. Then if I look at the y, t, and omega, then I want to define this as g of t, x, t, and omega. Yeah, so that's the stochastic process. That's the Zito process. Then, yeah, this is then now a p-dimensional. This is a p-dimensional. Zito process. And I can compute its representation. So the yk, so the case component. Yeah, maybe I should also write this as follows. So yeah, now the p. So yeah, you should not confuse this notation with the components with the notation with the time, but it's just in one dimension. It's easier to have the time as a lower index, and here it's easier to have the component as an index. But I guess the difference is always obvious which notation we use. So yeah, so now the time derivative stayed the same. Then I have to differentiate with respect to all xi components. So the x lives on Rn, so it has n components. And then I have the xi derivative, and then there's the additional term, where I sum over all n d squared dk dxi dxj dx dxi dxj. Now I have to explain to you how to compute this. This is the same as before. So now you should think all components of Brownian motions are independent, but times are not independent. So where dvi dvj is equal to delta ij dt, and the other thing we have is that the dt is the same as dt dvi dvi dt, and these all vanish. Okay, so that explains to you how to compute this product here. And so that's the multidimensional Ito formula. And then we will now come to, as I already said before, to the stochastic differential equations we want to look at. There will be two types of solutions, and then we also want to briefly discuss the type of existence and uniqueness statements we have there. Okay, so I guess we should take another picture before we start now with this other part. Okay, so the next part will now be solutions to stochastic differential equations. And existence and uniqueness. Yeah, and then on the homework we will also discuss a few examples of the stochastic differential equations, and you will learn to play a bit with them, apply Ito's formula, and see how this can be used to solve them, at least in some simple cases. Of course, you know that from the differential, from the deterministic differential equations that already there, it's not possible to solve all kinds of differential equations. So one And here it's of course even a bit harder because this integral starts being more complicated. So in some sense the number of integrals you can compute resembles a bit the number of stochastic of differential equations you can solve. Okay, but now we want to consider the existence and uniqueness of solutions to the following type of equations, to stochastic differential equations, which I write now again in this short form. They will look as follows. So I have a dtx, dxt. Then I have a coefficient alpha, which comes in front of the differential with respect to time, and sigma of t and x, which is in front of the Brownian motion. That's one I want to call star. And now we have the following setup. So for now we assume that the x is n-dimensional, then alpha is also n-dimensional, sigma will be a matrix, and B will be a vector Brownian motion, or Brownian motion on Rm. So where x is n-dimensional, B is an m-dimensional Brownian motion. And yeah, now I just want to work on intervals, maybe. So alpha goes from this interval 0t times Rn to Rn. And as I said, sigma is matrix valued. So that goes from 0 to t times Rn into the Rn times Rm matrices. And yeah, of course, we have to assume that they are measurable with respect to the product sigma algebras. Okay, and then the important point is that we will distinguish two kinds of solutions. So basically the now there are two types of solutions. So the first solution is somewhat the strong kind of solution, means that we start on a fixed probability space and all filtrations and everything is given to you, and the Brownian motion as well. And then you want to solve this equation on this given probability space with respect to this Brownian motion. So that's the strong solution. And the weak solution means that you just look at this somehow as some kind of abstract relation without fixing the probability space and the Brownian motion first. So that means someone gives to you this equation, and then you say, well, I can solve it. I can solve it in the following way. I can give to you a probability space, a Brownian motion, and a filtration, such that this equation is satisfied. And yeah, of course, you can give them. You have to give them an x, such that this equation is satisfied. And these are two different types of solutions, and they will have different implications in the sense of the types of existence, or more importantly, uniqueness results that we have. So now, if I didn't, this is now definition 3.9. So that's what it means to be a strong solution. So strong solution of star. Well, maybe I fixed this interval, and then, as I said, we also fixed the given Brownian motion, and And in some sense, also the filtration is fixed, that we will see next. So given the probability space, so that's the standard probability space we work on. And we also fix the Brownian motion. Brownian motion B, bt. And the initial condition is also fixed. And the initial condition xi, so that's of course a random variable. And then the only thing that is not given is this process xt. That's the solution that we want to find. And yeah, we assume that it has to have continuous past. Yeah, so maybe now is a good time for a picture. And then I give you another picture that you can see the full definition. That will now have 4 parts. So we have the following. So yeah, as I said before, it has to have continuous paths, and we also want to have the following properties to be satisfied. So the first property is that the process is adapted to a certain filtration. So it's adapted to the filtration. Yeah, this might look now a bit complicated, and the point is that one has to complete, or one wants to complete this filtration in a certain sense. So that's for some technical reasons to make everything well defined and continuous. So yeah, this is a filtration ft, and it's generated by the sigma algebra gt and the set n, which are given as follows. So gt is the sigma algebra that's generated by the Brownian motion for s smaller than t, and your initial condition gt, xi, and then the n is the set of all is the set of all sets that are contained in a null set of G infinity. So I have a G. So I take all sets in my in the basic set where the probability space is defined, and I take all sets which have a bigger set, which is measurable and which has measure 0. And P of G is 0, and yeah, maybe I should mention here that the G infinity is the union of all GTs. That's again a sigma algebra. Okay, so yeah, that's what is meant by completion, because now you have all null sets, and that makes certain arguments a bit easier on the technical level. So yeah, this you should not worry too much about. It's important that you say that, well, there is a filtration, yeah, which is given by this, which makes it yeah, such that the solution has to be adapted to this filtration. That's the important part, and also the BT will be a martingale with respect to that. Then the other thing is that almost surely you want to have that your process satisfies the initial condition. Then the third part is that it's a regularity assumption, so that the integrals make sense. So what do I need for that? I need that if I integrate alpha s xs plus sigma ij s xs, and this I need absolute value squared. Yes, this is finite with probability 1 for all t in 0, 1, then 0t, and for all I in j. And then, of course, the fourth condition is the most natural, well, is the one that so that means that the integrals are well defined in the differential equation. And then the fourth condition is, of course, that the integral version of this star is satisfied. Satisfies the integral version of star, so which was within the differential equation above here. And yeah, and this we want in an almost true sense, and for all t in 0t. Okay, so that's what that's the definition of a strong solution. So yeah, we have to be adapted to the filtration. We want that the initial condition is satisfied, and we have some regularity assumptions such that we can define the integrals corresponding to these two differentials, yes, and then of course the x has to satisfy this resulting integral version of the differential equation. Okay, so that's a strong solution. I guess that's quite natural. So maybe you can take a picture now. And then for the weak solution, we will have the same, well, essentially the same kind of results, but now you're allowed to change the probability space, and you're also allowed to change the Brownian motion. So you can, so in some sense you just start from the equation and you look at it in an abstract sense, and then you want to construct the probability space and the Brownian motion such that you get the solution. Okay, so that will look as follows. So that's the next definition, which is then the weak solution. So a weak solution of star is a tuple. So now it consists of multiple objects. Before, the essential object was just a stochastic process xt, but now we have this stochastic process, which will be the solution. Then we will have a Brownian motion, and we will have a probability space. Or maybe the order should be a bit different, but let me write it. Let's stick to this, and then we will have a filtration which satisfy the following. So, well, the first and the most important part is, of course, well, the most fundamental part is that this here is a probability space, and ft is a filtration on this probability space, and ft is a filtration F. So in particular, all the FTs are sigma algebras and are subsets of the F. And then xt is a continuous process. And yeah, I want it to be Rn valued as the equation. And it has to be adapted to this filtration ft. And bt is a Brownian motion, an n-dimensional Brownian motion. Is a Brownian motion on this probability space, and the martingale with respect to this filtration ft. Right, so that was these are somewhat the conditions that allow us to define the integral. the integral version of this star. And then we also need that 3 and 4 of the previous definition hold. So these are then that the equation is satisfied in the sense that it's 3 and 4 of definition 3.9. Are satisfied. Okay, so yeah, the main difference is that while in the so yeah, maybe now you want to take another picture. So the main difference here is that while the weak solution while the strong solution is on an a priori given probability space with a fixed Brownian motion, a weak solution is with this tuple, is defined as these. Well, you also need to have the stochastic process, of course, but also you can decide or you can choose one probability space, Brownian motion, and filtration that are for some sense convenient for you. So you can somehow change the probabilistic setup in some sense, as long as the coefficients of stay the same. Okay, and now I will finish this section by looking at some existence and uniqueness results for these kind of statements. So that's theorem 311. So we choose alpha and sigma as before, and we require some additional regularity assumptions. Satisfy for some, now of course everything needs to be independent of t, all constants. And then I want to have the following bounds. So alpha t and x, well, it's a vector, I need a norm, and the sigma is even a matrix. So matrix norm, they should grow as most linearly, and I need some Lipschitz continuity. So at least in the space variable, say this is smaller than c norm x minus y, and this should be true for all x and y in Rn, and for all t in 0 big T. So we want to solve the equation on this interval 0 to t, and yeah, we want to have an initial condition which is independent of this g infinity. So there's somehow there are no kind of correlations between the Brownian motion that we choose and the initial condition. That would of course make our life much harder. And we assume that the second moment of this initial condition is finite. Now the vector. So this is finite, and then we will find a strong solution. Then we find a strong solution. Yes. Then there exists a strong solution xt in 0t of this star. Yeah, maybe I should indicate the initial condition, so that's satisfied almost surely. That's in some sense already in the definition of a strong solution. And then the other thing is that we know that this thing is regular in the sense that I can, I take the correct, so sorry now. If I integrate the past and then of the solution, and I take the expectation of this, then this is finite. So that's some further regularity condition. So that gives me the existence. And now I can specify the sense of uniqueness I have. Namely, I have the following. If xt is another strong solution of this, is another strong solution of star, has the same initial condition, then we know that x and t have to be also, they agree almost surely. So t, y, t, the same for all t in 0t with probability 1, right? So that's now the second part. That's the uniqueness statement. Okay, so let's go through this once more. Maybe you can also take a picture in the meanwhile. So we need some regularity. So the alpha and sigma are again as before. So they're alpha is a vector valued function, sigma is a matrix valued function. They're measurable with respect to both coordinates x and t. And we have a growth condition so that they grow at most linearly. And we have a Lipschitz condition in the second coordinate. So these are in some sense very analogously to what you might remember from existence and uniqueness results of differential equations that are non-random. Then we have an initial condition that's independent of the g infinity. So that's everything that's related to the Brownian motion and then we have some regularity assumption on this, and finally we need that then we get that a strong solution exists, such that also in this kind of sense the second moment is finite. That's of course the expression that you also see in the Ito formula, in the Ito isometry, and you also have the you have a uniqueness in a very strong sense, namely that that two strong solutions with the same initial condition have to be almost surely identical. Okay, so that's the kind of existence and uniqueness of strong solutions. And now I want to see, and now the last part here will be to see what is what kind of uniqueness do we have for two weak solutions. Of course, if you have two weak solutions, then these kind of strong, this we'll do in proposition 3.12. If you have two weak solutions, then you cannot formulate it in that way, because you somewhat have different probabilities. So both solutions might live on different probability spaces. So you cannot really compare two random variables. But what you can say is that these processes, their finite dimension, what's called finite dimensional distributions, are the same. And that's in some sense that classifies when two stochastic processes are the same, or that they have the same law. Okay, let's go through this. So we assume that alpha and sigma satisfy the same conditions as before, as in the previous theorem. So, and now the point will be that I assume that I have two strong solutions, two weak solutions. So once I have the whole family here as before, and then I have the same kind of things with heads. So T, E, T, head, T, omega head, F head, P head, T in the probability space, and then also the filtration has a head. Okay, so these are two, now it's important that they're weak solutions. Of this initial string star, then they are the same in law. So what does that mean? So as I said before, while two stochastic processes are the same in law if they are finite dimensional distributions are the same, and they look as follows. So if I take the probability that a tuple, xt1 up to tk, and then also the Brownian motions, maybe I evaluate them at s1 up to sl. If they're in A, that's somehow a finite dimensional distribution. So you evaluate the stochastic process at k times, and then you ask what's the probability that this lies in a certain set, in a certain measurable set A. Then this should be the same as the same expression with when everything has a head. So xt head, xtk head, and then bs1 head, bsk head. It's in A. And yeah, well, now this holds for all k and l, t, I, s, j, and a r, k measurable. Yeah, A is a subset of r to the k plus l, and it has to be measurable. And yeah, I guess you know it's natural in which space they live. So yeah, in some sense, whenever I ask a probability question about these weak solutions, then they are the same. Okay, and then maybe before the Easter break, so yeah, I guess you know that next week there's no lecture. I want to give you a very brief, just a few lines outlook what we want to apply this to in the Hermitian setup. So outlook to the next lectures. So we still will probably need a bit more results from stochastic analysis to prove this, but then in the end what we will interested in is are the following two theorems. So so beta is positive, and sigma is the set of n-dimensional vectors such that the components are all ordered and different. And then I want to say that there exists a unique strong solution lambda t of what is called the Dyson-Brownian motion, and this is it has continuous paths, and a priori it lives in the closure of this set, and that's the unique strong solution of the following: d lambda I is the same as Brownian motion plus, and now there's some other term. Yeah, with this initial condition, for just some initial condition. And the very interesting feature is that, yeah, maybe I should also say that, yeah, lambda t has this component, lambda 1 up to lambda n. And the interesting thing is that lambda t actually lies in the inside, so as for all positive t. So as soon as you start having a positive t, then this kind of process starts separating eigenvalues, even if a priori some eigenvalues would have been the same. So of course you should think of lambda 1 up to lambda n being the eigenvalues of a Wigner, of a matrix, say, and then you start running. Well, of course we want to have a Hermitian matrix with real eigenvalues, and then you start running this thing here, which is called Brownian motion, Dyson-Brownian motion, and maybe I give this a star, and then the other theorem which will help us to study this thing in the eigenvalue setup. Then, well, if ht, which I write as follows, is a strong solution of the following equation. So EHIJT is 1 plus delta IJ. No worries, I repeat it again. I just want to give you an idea of what we want to apply all of this formalism to. dt for all I smaller than j and ji is made Hermitian. Then the eigenvalue process of this eigenvalue process of ht solves this star with beta equal to 1, right? And yeah, in the weak sense. So let's go through this again. So yeah, here I said that if I start from eigenvalues, then we will analyze this flow, and then at least the first thing will be that we show that we start separating eigenvalues, in particular because here you have this repulsive term where when I and j become close to each other, then they start having a force which separates them. And then the second theorem we want to prove is if we analyze, if we let stochastic process evolve on the matrix level with respect to this equation, then we will get that the eigenvalue process of this ht solves this this equation. And these two observations, they will give us a way to analyze the universality for random matrices, namely by we start from we'll start from running this process on the matrix level, and then we can analyze the eigenvalues and compare them to the eigenvalues of GOE and GUE. And this will be another tool to study universality. And yeah, that will be the program now for at least next few weeks to prove these two statements, and then to go from these statements to apply them to prove universality statements. Okay, then yeah, sorry for running a bit over time. If there are no more questions, then we can make a short break and continue with the exercise session maybe at 20 past 11.